Okay, let's check out this Snapchain contract. Up here on line one, you can see some imports. The keyword in Rust is use, but it's similar to keywords like import or require. Basically, you pulling in some stuff you need to use in your contract, right? So the Silverbot SDK is pretty much going to give you everything you need to, build your smart contract and interact with on-chain data. Some things you might not be familiar with are the concept of macros in Rust, but these are basically helpers that kind of like generate some really useful boilerplate code for you. The first main thing we see here is a enumerated type named storage defined, right? So by default, variables in Rust are private, but if you need it to be public, you just use the pub keyword, right? Basically, anything you want accessible from external modules, they either need to be public. In Rust, an enum or a enumerated type is, a fixed size list. It's a set of possible variants, right? So the storage is a type, and then we have one variant named check that's associated with a unsigned 32-bit integer. So basically, this storage type is going to function as a key for storing data on chain. So it's basically this integer is going to be the key for a message stored on chain, right? So one could be the first chat message, two could be the next chat message, right? But then above that statement, you'll see what's called a contract type macro, which looks like what's called an annotation in a lot of languages and frameworks. Basically, macros are a way to generate boilerplate code. In this case, contract type generates conversions between the way we want to store data on chain in like a really efficient way and the way we're going to deal with data externally. For instance, in a browser or any number of systems. This is basically contract type will create best practice conversions. I'll get your data on chain and off chain without you having to worry about the nitty gritty details. I mean, if you're really interested, you could perform what's called a macro expansion. I think it's commands cargo expand. But yeah, basically, you're just creating all this best practice code to safely convert data for on-chain storage and for getting that data off-chain. And then on line 10, we can see that we're defining a strut. And a strut in Rust is basically, it's like a data structure, right? It's like a grouping. It's a type that's a container for other types, right? So in this case, we're defining a type named chat message that contains 3 members, right? So for a message, we have an author, we have the message, the actual text being sent, and then we have a timestamp, which is, in this case, just a basic Unix timestamp. Addresses in Rust are, they can either be like an actual account, it could be like your wallet, or it could actually be a deployed contract. In Silverbot, addresses are really powerful because you can actually use it to enforce authorization, right? So later in this contract, we're going to call this require auth function, which basically attaches, some best practice sensible defaults for security to make sure your functions are being invoked in a predictable way that's safe and secure. And then again, we see this contract type macro, right? So again, this chat message is representing the data structure for data we're going to store on chain, referenced by that storage key that we defined above. And basically, just again, it's creating conversion code for getting that data in the right format for storing it on chain, and then pulling that data out in a format that's more flexible and universal. On line 16, we can see a constant named index. So like many languages in Rust, the The convention is to have a constant in all caps. In this case, we have a constant named index of the type symbol. You can think of symbol as a variant of a string, but it has a limited character set. So basically you only can use letters, dash, underscore, and it can only be up to 32 characters. It's a really good choice when you have a short identifier, like a key, for instance. Symbols are especially efficient if they're less than 9 characters. And then on line 19, we're defining a public struct named contract, right? So this is the type that represents our contract, right? So the contract macro basically says, well, this type, it's going to have functionality attached to it from the contract implementation, from the actual logic you define. And then there's going to be an interface for interacting with that implementation, right? So this is a pattern we see all across programming where you have an interface. Here's all the different ways you can interact with this system. Defining functions, what you get to pass into those functions as parameters. But then you also might have a client interface, right? So this client will be able to interact with your contract in a type-safe way. And it also helps you out when you're trying to write unit tests for testing out your contract. And then we get to the actual implementation, right? So the implementation is where you actually define the specific logic that's going to be executed when you invoke a contract function. In this case, our contract has a single function named send. This contract impl macro basically takes your defined implementation and it exports it to be publicly accessible, right? So any functions you want to be callable as a function invocation on the Stellar network are going to be defined in this contract impl. Using the keyword fn, that's how you define a function. And this function is named send, which takes in 3 parameters. So this env, or environment parameter, is something that you need to include. If you take a step back, you look at the Stellar network, contract invocations are basically executing arbitrary code, right? So you can write whatever you want in a function. So to allow this in a safe and secure way, basically you want to make sure this arbitrary code execution happens within certain, let's call it guidelines, right? So basically the env struct provides defined ways of interacting with on-chain data. For one, it contains data about the current function invocation. So it's okay, this is who invoked it. This kind of allows me to perform auth checks, but then it also provides Rails, or it provides a standardized, secure way for retrieving and storing data on chain. And then the address gets passed in. That's basically who invoked this function. And it's going to define, maybe it's a wallet that just executed a transaction with an operation called invoke host function, or it might be another contract. So in your front end, you would have a contract client that would invoke this function and then sign that transaction with the signer associated with this address. And then you have the Sorbonne SDK implementation of strings, which allows you to store text on-chain in a safe and secure and efficient manner. And strings are just arrays of bytes, essentially, right? Now on line 24, we have this function called require auth. Right, so when calling this function on an address parameter, basically it's going to ensure that basic sensible security defaults are attached to this function invocation. So, basically you think of it like you don't need to be a smart contract security expert to maintain the security of your contract, right? So for more advanced use cases, you might have to do a bit more, but for a lot of use cases, generic off-the-shelf security practices are going to do what you need to ensure that your contract is invoked in a predictable, safe, secure manner. On line 26, we're defining a variable named next index. By default in Rust, variables are actually immutable, so you can't change them. But if you need to change a variable in that scope, you could use the mute keyword, which identifies a variable or a reference as mutable, as changeable. Right? And it's an unsigned 32-bit integer, like the index we defined above. Now we can see how we're using the environment type. So basically we're calling storage on env, and storage provides us with functions for retrieving and storing data on chain in like a predictable, safe way, right? So anytime you want to store or retrieve data, basically you're going to follow this pattern. So there's a bit of nuance to storing data on Sorbonne that might be a bit beyond the scope of this video, but basically you have three types. You have instance, you have persistent, and you have temporary data. So you can think of instance storage as maybe like globals in your contract. Basically, instance data is going to be loaded every time a function on your contract is invoked. So the things like who is the admin on this contract? Things that you're going to need every single time you invoke a contract. You're going to want that in your instance data. Also stored in your instance data is your actual contract code. So your deployed WASM or WebAssembly code is actually also stored with what's called instance durability. I'll include some links that can help you choose the right type of data. But generally, for most data, you're going to choose persistent. And then in certain cases, for short-lived data, maybe temporary. An instance data is, you can think of it as like a small cache that stores important data that's needed pretty much every time you talk to the contract. And then we call the get function. And basically what you pass in to this function is a key to look at data stored on chain. So earlier we defined index, which is a pointer to the current index of the messages we're storing, right? So if we had 3 messages, we're getting this index, which will tell us where to store the next message when that comes up. And it can also essentially function as the length of let's say, well, it's not stored as an array, but basically it's a count of the number of messages stored on this contract. This unwrap function may be unfamiliar to people who haven't wrote a lot of Rust, but basically in Rust, there's not a concept of null. so basically you're gonna have to handle the case where data does not exist at compile time. Which is good because then you won't get any surprises at runtime. In this case, we're saying, hey, look up this data. If you don't find it, just set it to 0. On line 28, we are actually storing data with temporary durability. If you only want to store data as temporary, where it's only valid or it's only valuable for a short amount of time. Most data you want to store persistently. So we're going to call this set function, right? And what you pass into the set function is the key by which you're going to reference data and then the actual value, what data you're actually going to store. In the future, when you need to look up this data, you would use that key. So this set function actually passes in a generic. So it can handle a bunch of different types. And generally, the type inference is going to be going to be really strong. It's going to be able to infer what the types are, based on the context. But in certain cases, like in a unit test where you need to perform an assertion, or in some cases where you need to store that value locally in a strongly typed way, you're going to want to also add in this explicit generic type definition here using the double colon notation and then the diamond notation representing my key is going to be of the type storage or a variant of storage. And then when I'm actually going to store the data is going to be a strut of the type chat message. And yeah, you know what fields are in it because I'm telling you the type. So we're defining the key as a storage enum, which is kind of like the namespace. And then you have chat, which is the variant. And the chat variant, as we defined earlier, takes in a U32, an unsigned integer. So you may notice there's a and symbol before the storage. So basically what this indicates is that the variable. So basically this marks a variable as a reference. This is a bit beyond the scope of this video, but I'll include some links for you to look it up. But basically in Rust, there's a concept of ownership. So this concept of ownership is unique to Rust. In a lot of languages, you have things like garbage collection, which is how you manage memory, how you manage pointers. Basically, ownership is a way to guarantee that you don't have dangling pointers, which is a funny phrase for saying avoiding memory leaks, right? So you have to be really conscientious about how you store data on chain. So what's great about Rust is this ownership system kind of prevents dangling references in all but the certain use cases. But basically, it's going to make sure that you don't have memory leaks. And it also deals with the problem of, let's call it global state and race conditions. So basically, in JavaScript back in the day, you would have a variable and anything in the UI could modify that value. So you might be working with a value and it gets modified out of nowhere and it's really hard to manage, right? So this ownership system basically just handles all the complexity of managing memory. It's going to make sure you don't have race conditions. It's going to make sure that memory and logic operates in a predictable way, in a way that you expect it to. And it's also going to make sure that you don't have a memory leak blowing up your application at some point in the future. But basically, a reference by default, so in Rust, variables are immutable, right? So when you pass a reference of a mutable variable, basically it's like a read-only reference or pointer to some value in memory. So basically it's like, here is the value, but you can't modify it. In the case of a mutable reference, you can only have one reference to that mutable, basically just to ensure that you only have one, let's say, function invocation, modify that data at a time. So just to review, data can only have one owner, and if you need to pass it to a function, generally you have to pass as a reference. And we can see here in the set function definition that it's actually enforced that references for the type of key and value passed in are actually references. And then we can also see we're passing in a chat message as the value to be stored, passing in the author message and a timestamp, which we actually pull from the environment ledger data, which gives us a Unix timestamp. Then on line 36, we increment that next index. So the next time this function gets invoked, it's like, okay, put the data at this key. And then we follow the same pattern, calling env storage instance set, and then we're setting the incremented value to the index key.